Okay, so just like they always say, um, variety is the spice of life. This is true in a wide range of categories, and statistics is no exception. So so as excited as we've been talking about descriptive statistics, both univariate and bivariate, we are just as excited, if not more so, to move on to talking about probability, and now a slightly new but very related topic, which is this topic of random variables. So random variables are these kind of abstract constructions based upon the rules of probability, based on the axioms of probability, and these random variables we'll see are going to be they're going to be really important building blocks for where we're heading in this class. They're going to be very important building blocks for statistical inference, and for the development and application of statistical techniques to solving life's problems. So it's kind of paving the way for these future chapters in statistical inference, which just between you and me, I am very, very much looking forward to.
So, what is a random variable? A random variable is essentially a statistical experiment, right? A random phenomenon that ultimately has a numerical outcome or numerical result. So, 3 different examples I put there. You might measure a patient's blood pressure after you give them a new heart medication. You might count the number of runs scored by the Phillies during a playoff game. Could always hope. You might record the price of a company's stock at the end of a business day, right? On a lot of levels, these seem like 3 very different examples, and in many ways they are, but all 3 of them do have one thing in common. They're all essentially random variables. They're all random phenomenon that at the end of the day have a numerical outcome. Now, if we let x be the numerical measurement of the previous example, then we say that x is a random variable. Now, there are 2 types of random variables. We need to be able to distinguish between these 2 types, because the way we handle them or the way that we treat them is going to be slightly different depending on whether they're discrete or whether they're continuous. Discrete random variables, these are random variables that this isn't a rigorous mathematical definition, so I'll be straightforward with regards to that, but it's a very good working definition, particularly for an introductory statistics class. And so our definition for discrete random variables are going to be they're random variables that take the integers or the whole numbers as values. They generally, for us, will take a finite number of values, but again, they actually don't have to. So if you're a dentist and a new patient walks into your office and you open up their mouth and you look inside, you can think of that as a random phenomenon. Particularly if you want to count the number of teeth that have fillings, right? They could have a perfect mouth, in which case there would be 0 teeth that have fillings. There could be 1 tooth that has a filling, right? And I think at most we have 32 teeth. So, right, the upper bound would be 32. It makes sense for this random phenomenon to take the value 0, 1, 2, 3. It does not make sense for them to take the values between the whole numbers. That is, it doesn't make sense for them to take the values 1.2 to say there's 1.2 teeth that have fillings, or 2.8 teeth that have fillings. Right. The second example might be the number of times we flip a coin before getting heads. Right? So it could take you 1 toss, it could take you 2 toss. We would actually say that this could in theory go to infinity, that this really has no upper bound. That's all we're really saying. When we say infinity, we're really just saying that there's no obvious upper bound to the number it might take. You might say that, it's really unlikely that it would take you 20 flips until you finally get a heads. And it's true. It's very unlikely. Probably would not happen. But mathematically, you can prove that there is a small, very, very, very small probability that it could happen. Right? So you say, okay, well, what about 21? It can't be 21. And of course, the devil's advocate would say, well, It's pretty rare and it's pretty unlikely, but it is possible that it could be 21. And really any particular outcome, even saying it takes you, say, 3,000 tosses, has a almost immeasurably small but non-zero probability of occurring. So we would say that this particular outcome, takes the values 1, 2, 3, all the way to infinity. That said, it makes sense for it to take one toss. It makes sense for it to take two tosses. It does not make sense for it to take 1.43798 tosses. So again, this random phenomenon is only taking whole numbers as its values. We can contrast that. With continuous random variables. Continuous random variables are random variables that take values over a continuum of numbers, So temperature during a day might be 90 degrees, might be 91 degrees, but could also be, say, 90.2 or 90.3 degrees. The weight of a walrus, Often our scales will only measure something like 3,000 pounds or 3,001 pounds. But if we had a precise enough scale, it is possible for a walrus to weigh something like 9,000.01701 pounds. Agreed? Or the percent of nitrogen in a legume subjected to a certain treatment for those legume enthusiasts in our virtual audience. Could be 60%, could be 61%. Again, if we measured it finely enough, it could be 60.3%. So again, notice that these are situations or random phenomenons where the values are not only the whole numbers, but also all the values in between them. They take values over a broad continuum of values. Now, random variables have associated with them certain characteristics or properties. Essentially three. Every random variable has associated with it a probability distribution, that's what we're getting ready to talk about, has associated with it a mean, and has associated with it a standard deviation. We'll talk about those as well. But before we do that, let's talk about probability distributions. The probability distribution of a random variable essentially tells us the values that the variable takes and the probability, the likelihood that it takes those values. Now, to be a valid probability distribution, these probabilities must be larger than 0, They can't be negative. And they have to sum or add up to 1. So, we'll start with an easy example. Let's say that X is the roll of a 6-sided die. Let's go ahead and find the probability distribution of X. And so here it is. I put it together in a nice tabular format. So the first column is X. Those are the outcomes. Remember, probability distribution is all the possible outcomes and the associated probabilities. So I put all the outcomes to the left. I could roll a 1, I could roll a 2, I could roll a 3, a 4, a 5, or a 6. I put the probability of those outcomes to the right. The probability of a 1 is 1/6. The probability of a 2 is 1/6. The probability of a 3 is 1/6, and so on. Slightly more complicated example. Let's say that we have an urn. I don't even know what an urn is, to be truthful, but they're used a lot in statistics or probability problems, and they're often filled with colorful balls. So let's go ahead and perpetuate this strange and unusual example. So we have an urn. It's got 3 red balls, 1 black ball, and 2 brown balls. And we play a super fun game. You reach in, you pull a ball out at random. If the ball is red, then you win $3. Wow, congratulations. If the ball is brown, then you win $6. And if it's black, oh my goodness, black is the money ball. If it's black, wealth and riches beyond your wildest dreams. $20. Oh my. Now, if X is the money that you win, what is the probability distribution of X? We'll do it on the next slide. Before we do that, it might be tempting to say X is the color of the ball. But remember, we actually can't do that. Remember, a random variable, is something that takes a numerical outcome. which is why I cannot say it's the color of the ball. Color is non-numerical. That's why I had to attach to every color a number. In this case, I attached to it a sort of dollar amount. I turned it into a sort of a betting game. Alright, so here's the probability distribution. X is the amount of money we can win. The left-hand column are the possible outcomes. We can win $3, $6, or $20. And the probabilities are along the right. So there was a total of 6 balls in the urn, 3 of which were red. Red is what gave us $3. So the probability of winning $3 is 3 out of 6. There were 2 brown balls. Brown is what won us $6. So the probability of a brown ball, the probability of winning $6 is 2 out of 6. Now there was only 1 money ball. There was only 1 black ball. That's what gave us, right, untold wealth and riches. $20 whole. So the probability, right, of an early retirement is going to be 1 out of 6. Third and last example. Let's say that the stock of IBM is currently worth $116. At the end of the day, if we hold on to it, it has a 20% chance of going down in value to 110. It has a 30% chance of going up in value to 130, and it has a 50% chance of staying the same. If X is the value of the stock at the end of the day, what is the probability distribution of X? Now again, this is definitely a simplification of the way a stock behaves, right? We would normally think that if you have stock that's worth $116 at the beginning of the day, at the end of the day there's a whole range of possibilities for what it could be worth. I'm simplifying it by saying that there's only 3 outcomes. But nonetheless, we could think of a stock as being sort of a risky asset, or being a random variable and having, right, uncertainty attached to, right, whether or not we're going to make money with it. So here are the possible values, right? It could go down to 110, it could stay at 116, or it could go up to 130. Probability of it going down was 20%. Probability of it staying the same was 50%. Probability of it going up was probability of it going up was 30%. Easy enough, right? Well, the second property, or the second characteristic of a random variable that I mentioned, is that every random variable has not only a probability distribution, but a mean. And we can use the probability distribution that we just talked about to actually figure out what the mean is. The mean of a random variable is also sometimes called its expected value. So we could find this mean, we could find this expected value using the following formula. So we abbreviate the mean, or we denote the mean with the Greek letter mu, and there's our add 'em all up symbol. So what we're basically saying with that terse symbolic formula is that the mean of the random variable mu is, I take every outcome X, I weight it by its probability, I multiply it by its probability, I do that for all outcomes, and I add those numbers together. Right? The mean is the sum of all values weighted by their probabilities. With a random phenomenon, we'll never know with certainty what will happen, but the mean tells us what we might expect to happen. Now this is a somewhat intuitive formula, right? Because why? Well, if a certain outcome, right, is very likely to occur, we should give it a lot of weight, agreed? And we do that by multiplying it by a relatively large number, by its large probability. If a number is very unlikely to occur, if it's a very rare outcome or very rare number, well, if it doesn't happen very often, we shouldn't give it a lot of weight. And that's exactly what happens, right? We multiply it by its, right, relatively small probability. So let's do this. Let's do this for our 3 examples. Let's start with our die roll example. So for our die roll example, right, the mean is 1 times the probability of rolling a 1 plus 2 times the probability of rolling a 2, right? And I had to do a little dot 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 there because I didn't have enough room to put them all out there, but I just sort of continued that process. 5 times the probability of rolling a 5 plus 6 times the probability of rolling a 6. Now in this case, all those probabilities are 1/6, so I have 1 times a 6 plus 2 times a 6 plus 3 times a 6, right, all the way to 6 times a 6. To simplify that calculation, notice that all those terms, all the numbers I'm adding, have 1/6 in common, so I could factor that out. That's the same as 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. If I add those numbers up, I get 21. So my answer is 21 over 6, which is 3.5. 3.5. Now, a common mistake that students make is to somehow round that to either 3 or to 4, to say, it doesn't make sense to say I expect to roll a 3.5 when in fact I cannot roll a 3.5. That's true, but nonetheless, there are a whole slew of reasons, and I'll talk about them in a little bit, about why it's so important to never round the mean. The mean can and often does take values that the actual random variable cannot take. That's okay. You should never round it. You should leave it to what it is. Example 2. Right? Same idea. The mean is 3 times the probability of winning $3, plus 6 times the probability of winning $6, plus 20 times the probability of winning $20. Right? Which, if I get those probabilities from the earlier slides, is 3 times 3 sixths plus 6 times 2 sixths plus 20 times 1 sixth. I get $6.83. We can interpret this. So one way, one nice way in this type of context, for this type of problem, of interpreting the mean, is we can interpret this as the fair price of this game. Right? I'm not going to let you just reach into this urn and pull colored balls out and just hand you money. I'm certainly not going to let you do that for free, right? I'm going to charge you for the privilege and the fun. And so the natural question is, right, if we were to sort of put together and conduct such a game, the natural question is, how much did I charge for that game? The expected value is a common way of answering that question. If I charge you less than $6.83, you're getting a good deal. And if you play long enough, remember, that's the key idea. We talked about this in Chapter 3. Probabilities and right, consequently random variables, these are sort of statements in the long term. If you play long enough, you're guaranteed, virtually guaranteed, to make money off me if I'm charging less than $6.83. If I charge more than $6.83 and we play long enough, I'm virtually guaranteed to make money off you. If we charge exactly $6.83, then we could play this game as long as we like. We could play this game to our heart's content, and at the end of the day we would expect to break even. Right? We would expect to walk away still friends with one another. Last example. So here the mean is $110 times the probability the stock's worth $110, plus 116 times the probability the stock's worth 116, plus 130 times the probability the stock's worth 130. If I do all those calculations, I get $119. So this can be interpreted as the fair price for this particular financial asset or stock. This is one of the primary ways in mathematical finance of pricing stocks. Yeah, it's a introductory way of doing it. There's ways of tweaking it and taking things like risk adjustments into account, but this is the basic idea of pricing these stocks. And so, right, if you could buy the stock for less than $119, you'd be getting a good deal. If someone's selling it to you for more than $119, right, it's a bad deal. You're getting ripped off. If it's $119, you would say that's a fair deal or a fair price. Now notice I actually didn't interpret the mean. I didn't interpret the 3.5 that we got when we talked about example 1. In that type of example, in a somewhat more general or somewhat more generic situation, when we're not talking about financial assets, or we're not talking about games of chance, how do we generally interpret the mean of a random variable? Well, consider the idea of repeating the random variable or the random phenomenon that the random variable is based upon consider that idea of repeating it over and over and over again. So in terms of example 1, right, consider rolling that die over and over and over and over again. And as you're rolling it, computing the sample mean. An interesting mathematical fact that's been shown empirically and can be proven theoretically is that we will observe that the sample mean converges towards a certain number as our sample size increases. That is, the more we roll it, the more we roll that die, as we compute its sample mean, the sample mean is getting closer and closer to something. What is it that it's getting closer and closer to? It's getting closer and closer to mu, the mean of that random variable. That is, the sample mean converges towards the mean of the random variable. So when I'm talking about that this is sort of like a sample mean, or what I expect a sample mean to be, it makes sense that it could be a 3.5, right? Sure, because, I mean, imagine if I rolled a 1 and then I rolled a 6. The sample mean is 1 plus 6 divided by 2. The sample mean is 3.5. It's perfectly reasonable for a sample mean to take the values between 3 and 4, because of the fact that we're dividing by the sample size. By the way, this is very analogous, or very similar to what? It's analogous to that idea of relative frequency that we talked about before, right? Right. This is essentially the same thing as saying that if you repeat a phenomenon over and over and over and over, you look at the proportion of times that some characteristic or quality is satisfied, that relative frequency converges to the true probability. It's really the same thing as saying that the sample mean for a random variable converges to the mean, the true mean, of the random variable. Now, just to conclude, every random variable also has associated with a standard deviation. We denote this with the Greek letter sigma. It's essentially a numeric measurement of how far we expect a random variable to be from its mean. Right? It's essentially a measurement of variation, dispersion, or spread. If that sigma is very large, and sigma is never, it's always non-negative. It's only 0 if it really just takes one value with 100% probability. So generally it's positive in any type of non-degenerate, interesting situation. And the larger it is, right, that means the farther we expect it to be from the mean, which sort of means the more variation, the more spread outedness, the more dispersion there is. Now, we could also square the standard deviation, and we can get something called the variance. So, right, every random variable also has a variance. They're related in the same way the sample variance and sample standard deviation were, as you can go back and forth between them. And just like we talked about in chapter 2, the variance of a random variable is in weird squared units, which means that we generally focus on the standard deviation, sigma, which is in the original units. Now, to wrap things up, do not confuse mu and x bar. Do not confuse sigma and s. Mu is the mean of a random variable. X bar is the mean of a sample. Sigma is the standard deviation of a random variable. S is the standard deviation of a sample. Mu and x bar, as well as sigma and s, they have important conceptual and computational differences. We saw the computational differences because we did a number of computations for mu. We didn't actually compute sigma. Its formula is a little bit tricky and technical and not worth the class time. It would just detract from the big picture. There is a formula for sigma. It is different than the formula for s. But more importantly than those computational differences are the conceptual differences. We'll have to wait until chapter 5 to really start talking about these differences. But for now, just train yourself, condition yourself that these are different things. Do not use them interchangeably, right? Because they are not the same thing and hence should not be used interchangeably.